upon PIV, we can decide which rectifier is good. That means we already seen that half wave is not good because efficiency. What happened?
ऋषभ कैमरा ऋषभ माइक ऑफ कर.
So already we have discussed that efficiency and ripple factor of half wave rectifier is not good. Okay, but the problem is in center tap transform, because we require the center tap transform, and in this type we don't require a center tap. Normal transformer can be used. Okay, so these are the things we know. So depend upon PIV, we can also quantify the rectifier. So PIV means, if you remember, we have discussed in diode characteristic. If you take the diode characteristic like this, reverse bias, this is your breakdown voltage. Okay, that means the point after which huge amount of current will flow, and this region is breakdown region, right? So we cannot control the current through them, so the diode can break. Just before that means the point at which the diode will break or huge amount of current will flow, just before what is the voltage, so that the diode will not burn, or it can sustain that voltage, is called as PIV, peak inverse voltage. Maximum means peak, inverse means negative voltage will apply so that it can sustain the diode. Now this is component wise, right? Now if this diode is present in any circuit, then that is also valid for the circuit. If diode will break, then obviously the circuit will break. Okay, so here you can understand like that. Here we can find a voltage. We know for forward voltage the rectifier will work, and reverse voltage it will not give any output voltage. But in case some negative voltage we apply, so what is the maximum range so that the circuit will not break? Okay, that we need to find out here. So you can see the definition what I have written. PIV is the maximum reverse voltage that can be applied to the diode, which can not damage the diode. So PIV rating of diode is very much important to design any circuit. So PIV or rectifier can be found as below. So to understand that, let me draw the diode circuit what we have already understood. This is your diode circuit, and from here we are giving AC. Whether transformer is required or not, we don't bother. So input AC. Okay, this is your load resistance, this is your diode. Now across this diode I want to find what is the negative voltage, or what is the maximum negative voltage I can apply. So negative voltage means, obviously I should bias the diode in negative direction, or negative voltage I should give. So negative voltage means negative half cycle if you give, then if you remember, because 3-4 concepts are combined here, we have discussed whenever the diode is in forward bias condition, we can replace as short circuit. Short circuit means current will be there and voltage is 0. Reverse bias means when the diode is connected in reverse bias condition, then it will be open circuit. So open circuit means, what is my current? 0. But I should get some voltage here across these 2 points. They are not shorted. So ultimately I need to reverse bias this diode so that I can find what is the maximum voltage across the diode. Okay, so that's why what we do, we try to reverse bias the diode. So when I reverse bias, then obviously the input voltage, input voltage will be negative. So here I'll give minus plus. Minus plus means, or plus to minus, if you go from this, then this is representing negative half cycle. So when I give negative half cycle, then diode will be on or off? In this condition,
Off.
off. Off means this is open circuit. So this is your open circuit. So I'll get some voltage across this. Let I assume this voltage is my PIV. Okay, I'm assuming this voltage is PIV. So this is negative, this is positive, and we are giving the voltage like this, input voltage. So this is your VM, this is your minus VM. So minus VM means I can say this is your VM. Plus to minus means automatically negative sign will come. When I apply KVL from here to here, I am moving from plus to minus, bottom to up. So it will be automatically minus VM. Okay. So once you understand that, I need to find out the PIV, means this voltage I need to find out. Okay. I don't know this voltage. I am representing here V as my PIV. So that's why I am writing here V as PIV. Now you can apply KVL in this loop. What is the current flowing across this open circuit?
0.
0. So what is the voltage drop across here? I into R. I 0 means voltage also 0. So if I apply KVL, then plus to minus, I'm moving from here. Okay. Then this is minus VM. Then this is minus, this is plus. So plus PIV. Then across RL, 0 equals to 0. Is correct or not? Any doubt? I'm moving from here, plus to minus, that is minus VM. Then here minus to plus, plus PIV. Then here across RL, this is 0. So loop is complete. So equals to 0. Is it understood?
Yes, sir.
Now I can easily calculate what is PIV. PIV equals to VM. Okay, PIV equals to VM. This is found. So PIV rating of half-wave rectifier is greater than or equal to VM. Either this voltage or more than that voltage. Actually, this is negative. So if you take that negative sign, it will be greater than. So you remember PIV of half-wave rectifier is VM. Okay. Now, if you follow the process, then we can also calculate for center tap rectifier. So center tap means, you see, this is my center tap rectifier. We have taken a transformer, central tapped. This is one diode. One resistor is connected here. Here another diode is connected here. This is your RL. So D1, D2. Now same case I will take minus plus. So I'll get here plus minus to make voltage. I'm making 2 voltage here. So here let us take VM. Here also VM. Which diode is on? Which diode is off?
So D2 on, D1 off.
D2 on, D1 off. Okay. So D1 off means it will be open circuit. Okay. And this one is short circuit. So short circuit means here voltage is 0. but here I'll get some voltage. So that voltage, let me represent here PIV. So here it is minus, here it is plus, and current is flowing in this loop. So this is plus, minus. Okay. So in the upper loop, current is how much? Here, open circuit current is how much?
0.
0. But at the same time, current will flow in this loop also, lower loop, because it is short circuited. So I'll get some current here. So this current into RL I'll get, and if I consider this D2 is ideal, then there will be no voltage drop. So the voltage what we are applying here at the input, that will be dropped across the RL. Now you apply KVL in the upper loop, plus to minus, here green line I am drawing, plus to minus, minus VM, then across open circuit, so that is plus PIV, then I am moving from here, then across load. So across load I'll get current or not? This is open, so I'll get current or not?
No current.
No.
Think again.
Yes, sir. Current due to the second diode, since that is in forward bias.
Yes. So it is the, you see the lower loop is on. So current will flow and it will move in this direction. Current will not move in this direction, but it will move in the load. So some current is flowing, means obviously voltage drop across the RL. Due to upper loop, I am not getting any current, but due to lower loop, I am getting current. So that voltage will be VM. So minus VM. Understood or not?
Yes, sir.
So what is my PIV? PIV is equals to 2 VM. Okay, 2 VM or greater than 2 VM you can write. The same way you can do also for bridge type. So let me show you that one. Last class we have drawn here. Here, what we have given, positive half cycle or negative half cycle, which one we have given? Positive half cycle we have given. You can also go for negative half cycle. Okay, so same thing, because two are on, two are off, we can also go for positive half cycle. So here if I am giving VM, I'll get VM here, and across this one minus plus, this is your PIV. Okay, so I'll get a loop here. Tell me what is your PIV if I'm moving from this point. I'm moving from minus to plus, so plus VM, then here voltage is 0, then here plus to minus, minus PIV equals to 0. So PIV equals to VM or not? Check it again. Current is flowing in this input transformer as VM. So if I'm moving from here, then across short circuit current is 0, voltage is 0, then open circuit PIV, and again I am moving in that same point. So it is a loop, no need to go through RL, because to apply KVL we need a loop. Okay, so plus VM minus PIV equals to 0, so PIV equals to VM. Is it understood? You can also take negative half cycle. If you take minus plus, this will be off and this will be on. You can also do that one. So same thing will be happen here. So if I show you, let me take another color here. So this is plus, this is minus. So this will be plus, this will be minus. Here also Vm. Here I'll get PIV minus plus. Now you can move in this loop. What will get? Plus to minus. Where I'll write. Let me clear this one. Plus to minus. Minus or plus? I'm moving
Minus.
minus Vm, then minus to plus, plus PIV equals to 0. Here it is short. So PIV equals to Vm. So same way you can calculate. Okay. Now, once we know the PIV, let us compare the three type of rectifier here. This type full wave rectifier. So how many diodes are used in bridge rectifier? 4.
4.
Transformer required or not? Not compulsory or not mandatory. You can use or you cannot use. Directly also you can take. Or for center tap, we must require a center tap transformer. Efficiency 81.2%. Ripple factor 0.48. Output frequency 2FN PIV VM. Okay, so PIV for bridge type and half wave rectifier VM and center tap it is 2 VM. So which one is preferable if I consider PIV? Center tap, because even if more reverse bias will give, that means 2 times of maximum voltage, still the circuit will not burn. Okay, that is only related to this PIV. But if you consider center tap transformer, this problem of this center tap means we must require a center tap transformer. If I don't have any center tap transformer, then I cannot design this rectifier. Then we must go for bridge type full wave rectifier circuit where 4 diode will be used. And obviously this half wave rectifier are no use because efficiency less, ripple factor less. Okay. Is it clear for all?
Yes, sir.
Okay. Now we'll move to filter. It's a very important concept. So let me first draw the input signal. What we have given. Output signal. Okay, 3 diagram I have drawn. Tell me what we have drawn. This is input. This is half wave rectifier output. This is full wave rectifier output. Yes or no?
Yes, sir.
So this is your pure AC. This is your AC plus DC. This is also AC plus DC. But from here to here, less AC. Okay, both are called pulsating DC, but we have seen in the ripple factor, its ripple factor is 1.21. Here it is 0.48. So you can assume a less amount of AC is present in my full wave rectifier output or pulsating DC. Now, actual requirement of my rectifier is constant output, which is this one. Okay, this is pure DC. Pure DC. So what is it in here? We have now used the diode to produce a pulse DC signal. Most equipment require regulated DC. Regulated DC means pure DC. We must remove the ripple. So whatever ripple we are getting, we must remove this one so that this AC must be removed to get pure DC. Okay, so this segregation means two things are combined, we have to separate them. Suppose in your household चावल में कुछ कंकर आ गया है, ठीक है, तो क्या करते हो?
उसको रिमूव कर देते हैं।
उसको रिमूव करते हैं, तो ऐसा कुछ ऑटोमेटिक कुछ नहीं है कि चावल और कंकर अलग हो जाए, तो मैन्युअली एक एक निकाल के फेंक देते
टूट जाए सर उसको।
हाँ है, ऐसा कुछ है जो मतलब चावल और कंकर को अलग कर दे?
नहीं सर,
हैंड पिक सर ओनली।
हैंड पिक, सो हम ऐसे अलग करते हैं. So that is, we can say that is one type of filtering process. Okay, we are filtering the rice and whatever sand or mud or whatever the things are there which is not rice, we are filtering. Okay, now here also we say whatever output we have received from the rectifier, that is having some part of or some portion of AC in my output DC. So we have to make one circuit which will separate this AC and DC, so that we can receive or we can use our DC, and this action or the circuit which is used to separate this AC and DC is called filter circuit. In fact, the circuit actually suppressing the AC and passing the DC. Okay, so that is your filter circuit. So if I take see here one circuit, rectifier, this is a block, inside that maybe half wave, maybe full wave. So here I have taken full wave because you can see this is the rectified output, and here I am giving the AC input. Now once I pass this rectified output to another circuit which is called as filter circuit, then I'll get pure DC. That means this filter circuit actually suppressing the AC and passing the DC to the load, passing to the DC to load. So the output of a rectifier circuit is not a pure DC or proper DC, but it has pulsating in nature that contains AC and DC component. The AC component is undesirable and must be kept away from the load. Now to do this, filter circuit is used, and the filter circuit which will filter out the AC component and allow only DC component to reach the load. The filter circuit is generally a combination of inductor and capacitor. Okay, so filter is nothing but a combination of inductor and capacitor. It's not like that something new, already you know the inductor and capacitor property. We'll use that property to describe this filtering action. Okay, so like resistor having resistance R, capacitor or inductor have some resistance or not?
Yes sir.
What do you call them?
Capacitive resistance.
Capacitive resistance? No.
Sir,
Any other
impedance?
name? Impedance. Impedance you are saying. Okay. Combination
Yes, sir.
of
Impedance.
impedance. Okay. So impedance means combination of all these when inductor, resistor, capacitor is there, and the effective resistance or combination of all the components resistance is called as impedance. And particularly capacitor means we say capacitive reactance, and inductor means inductive reactance. Okay. And do you know what is the representation? How will represent this capacitive reactance or inductive reactance? Do you remember this XC and XL? Have you used this notation earlier?
Yes, sir.
Yes, sir.
So what is the value? What is the formula for this XC?
Don't.
Yeah, the-
याद नहीं सर.
याद नहीं है. For XC it is 1 by 2 pi FC or 1 by omega C, and XC means it is omega L or 2 pi FL. Now you remember something? 1 by omega C omega L. कुछ
Yes,
याद
sir.
आया? कुछ याद आया?
Yes, sir.
Now you have studied this one in plus 2 level. RLC circuit उसका impedance कैसे निकालते हैं, frequency, resonance ये सब पढ़े हो. So same concept we will use here. Okay. So let us try to understand this XC and XL in terms of this AC and DC. Let us take a DC signal. Okay. So DC means what is frequency? DC signal, what is the frequency of the DC signal?
0.
0. Now, if I find XC, then what will get? 1 by 2 pi, in place of F I'll put 0 into C. What is the answer?
Infinity.
Infinity. That means if I pass DC signal through capacitor, it will have infinite impedance, or it will oppose the DC signal with infinite resistance. Am I correct? Can I conclude that from this X equals to infinite?
Yes, sir.
When I pass DC signal, then this DC signal will be opposed by this capacitor with infinite impedance. Okay. Or I can say capacitor block DC. If it will give infinite input impedance or infinite impedance, then the DC will not pass through the capacitor. It will block by this capacitor. Can I write like this?
Yes, sir.
Now we'll take AC. AC means it will have some frequency. Okay, not 0, it will have some frequency. So XC, I'll find it will be 1 by 2 pi FC. So it will be finite, will not infinite, because F's have some value. So compared to this, it will allow DC or not?
Yes, sir.
So I can write capacitor allow AC. So these are the two conclusion statement I can combine to one: capacitor block DC and allow AC. Capacitor, block DC, allow AC through them. Is it clear? Or any doubt? अरे क्लियर ना, कुछ डाउट है पूछो, नहीं तो
सर एक बार फिर से.
DC means frequency 0. Okay.
Yes,
XC
sir.
formula we know 1 by 2 pi FC. So I am replacing in place of F as 0. So it is giving you infinite. Okay. That means if I pass DC signal, suppose this is a capacitor and it offers XC as infinite. Now if I pass DC through them, will it pass through this capacitor offering this infinite impedance?
No, sir.
No, sir.
So what I conclude here, capacitor, block, DC. Now if I take any AC signal, it will have some frequency, maybe 50 Hz, 100 Hz or anything, but it is not 0. So if I calculate XC, then it will have finite value. So I can say capacitor compared to DC, it will allow AC. अगर ये infinite नहीं होगा, finite होगा, तो definitely it will resist, but some part is passed.
Yes, sir.
Infinite मतलब ये कुछ भी नहीं छोड़ेगा, but finite होगा तो थोड़ा बहुत अपोज करेगा, थोड़ा बहुत अंदर भी जाएगा. ऐसा नहीं है कि सारा चला जाएगा, कुछ ब्लॉक होगा, कुछ पास होगा. Okay, so you can assume compared to this blocking, it is allowing. This is only comparative statement. It is not perfect. Okay, I am not saying that capacitor allow AC means it will fully allow AC. It will have infinite, finite impedance means somewhat like resistance. It will oppose some current, but some current it will allow. Okay, this is only comparative statement. Now let us consider this XL. Same thing I will take for DC. XL frequency is 0. So XL how much? 2 pi FL, that is 0. Yes or no?
Yes, sir.
So whenever I will pass DC through a inductor, this is my inductor. If I pass DC, then do it have any opposition, or will it offer any resistance?
No, sir.
No, zero resistance. So zero resistance means DC can easily pass through inductor. So I can write inductor allow AC. Is my statement correct?
Yes, sir.
Now if I take AC, sorry DC na,
Inductor allow DC.
DC.
AC. Now let us take AC. So AC means it will have some frequency. So frequency means XL will be equals to 2 pi FL. So it will be finite. So earlier it is not offering any resistance. Now it is offering some resistance. So I can write inductor. Here also it is comparative, not absolute. Conductor, block, AC. So I'll combine both the statement here. Capacitor, block, DC and pass. AC, inductor, pass, DC and block, AC. Just opposite or not? You see this statement and this statement. So what is my conclusion? Capacitor block DC pass AC, inductor pass DC block AC. Okay, now we'll go to the filter circuit. So whatever I have explained, that same thing is written here. A capacitor pass AC but does not allow DC or block DC. Inductor pass DC but does not allow AC. Now we'll see type of capacitor. So using this L and C only, the capacitor filter, inductive filter, LC filter, pi filter are designed. So first one is capacitive filter where only capacitor used. Second one is inductive filter, only inductor used. LC filter, combination of L and C. LC pi means the structure is like pi. We write pi like this. So the structure is like pi. So it is called as LC pi filter. So capacitive filter first we'll see. Okay. So see here, I am drawing the rectifier. The rectifier is like this. So what I'll do, I'll put capacitor across the load. Before load, I'm putting the capacitor and I'm removing this diode. So we'll take up to, or I can say, I'll take okay, this part I'll not use. I know the output of the signal is like this. Okay, so that's why I'm only taking this part. So let me again redraw that one. Okay, plus minus V naught, this is your capacitor, and this is the rectified output. What is my rectified output? My output is like this. Like this. Okay. So this is your, let us take V naught and this is your T. Now see, this is your AC plus DC. First we'll see common sense, then we'll go for charging and discharging of capacitor. Two way we can understand this concept. So AC and DC is given to here. Okay. Now when AC and DC is given, it is flowing in this direction, then it is flowing here. So across capacitor, what we have known, capacitor blocks DC, pass AC. Yes or no?
Yes, sir.
So across the capacitor, the DC will be blocked and AC will pass to resistor, and across that, because all the circuit are ground, it will be grounded. And capacitor is connected parallel to the resistor. So here, whatever voltage I'll get, the same voltage I'll get here. So V naught. Understood? AC is bypassed to ground and capacitor will hold the charge, or DC, capacitor parallel to resistor. So whatever voltage will there in the capacitor, same voltage I'll get across resistor. So in that way, the AC is grounded, I'll get only DC across the output. This is one way, means just now whatever the concept we have learned, this is one way. Other way is, what is the property of capacitor? Capacitor will charge and discharge, yes or no? Capacitor will charge fully, then discharge. So whenever I am giving the signal here, let us take I am here. So I am giving this one to this circuit. Now when I am giving this one to this circuit, then this is increasing. This is increasing means across the capacitor it is charging. We are supplying to the circuit the voltage. What voltage? This voltage. So it will charge, the capacitor will charge up to what? Up to this point. Yes or no? This capacitor will charge or not? When I am giving this input voltage, the capacitor will charge or not?
Yes, sir.
So up to what it will charge? Maximum voltage, maximum input voltage. So
Yes, sir.
maximum input voltage it will charge. Once it will charge, what will happen? कैपेसिटर चार्ज होने के बाद क्या होगा? फुल्ली चार्ज हो गया, फिर उसके बाद फिर डिस्चार्ज होगा कि नहीं होगा?
डिस्चार्ज होगा वोल्टेज कम होने के बाद बाहर का।
डिस्चार्ज होगा। डिस्चार्ज होने के लिए उसको एक पाथ चाहिए, है कि नहीं? ऐसे तो डिस्चार्ज नहीं होगा ना, किसी के थ्रू ही डिस्चार्ज होगा, ग्राउंड
Yes,
होगा।
sir.
So across source means from here, this side we are providing source. So again, it will not discharge through the source because already we are providing some voltage here. So once it is charging up to, let us take this is Vm. Okay. Once it is charging up to Vm, I'm getting the voltage here Vm, then it will start discharging. So it will not follow the same path like this. So it will find another path. So what path it will find? It will find a resistor here. So across load resistance, it will try to discharge. Okay. So when it is discharging, it will have some time constant. So time constant is RL into C, where C is the capacitor, RL is the load resistance. And you know this load resistance value is high. That means in kilo ohm resistance. So the time constant is also high or large time constant. So large time, what do you understand by time constant? Tau equals to RC, you know, for RC circuit. But what is the literal meaning? What you understand? क्या समझ में आता है time constant बोलने से? Anyone? Don't know. Time constant means the time taken to charge or discharge. Okay, how much time it is required to fully charge or fully discharge? That is time constant. So here, if I find the time constant, it is RL into C, and if time constant is more, I can conclude it will take more time to discharge. Okay, it will take more time to discharge. So due to that, what happened? See here. Suppose I will take this waveform, and initially it is charging like this. Now once it is charging, let us take time as 0, 5, 10, 15 second. This is in second. Okay. Now to fully charge, almost I will take 2.5 second. Now discharge also I should take 2.5 second. Yes or no?
Yes, sir.
Now if I say this discharging time due to this RL, because it is discharging through RL and RL is high, instead of 2.5 second, it require let us take 7 second. That means from Vm, let us take 5 volt to discharge or to move from 5 volt to 0 volt, it requires 7 second. Instead of 2.5 second, it will require 7 second. Okay. So can I reach here or 0 volt after 5 second? Are you getting my question?
Yes, sir.
इसको डिस्चार्ज
Sorry,
होने
sir.
के लिए normally the charging is 2.5 second, discharging is 2.5 second, but ये इसके थ्रू डिस्चार्ज नहीं हो रहा है, लोड रेजिस्टेंस के थ्रू डिस्चार्ज होगा, जिसको 7 सेकंड चाहिए फुल्ली डिस्चार्ज होने के लिए. तो जब मैं 2.5 सेकंड के बाद देखूंगा तभी ये कितना वोल्टेज रहेगा, 0 वोल्ट रहेगा कि कुछ और वोल्टेज रहेगा, मोर देन 0. बोलो
सर कुछ और
0 नहीं रहेगा.
नो सर.
Okay, so that I can draw like this. The charging will be not follow the pink line, it will follow like this. Okay, some value will be here, or I can say this if you count here, this is 2.5 and this is 5, so 7.5 second is required to fully discharge, and I am writing here 7 means it is not 0. Okay, let us take 6 means it will be somewhere here, or 5 means somewhere here. Then again it will start charging, again it will discharge like this, again charge, again discharge, it will continue like that. So actually I am detecting this envelope. Okay, now you see, if I increase the RL, more and more RL, I'll get more wider envelope like this. Now compared to this pink line, let us take this is 1, this is 2, this is 3, where ripple is reduced. किसमें कम रिपल है?
3 में आई थिंक सो सर.
3 में.
यस
ठीक है. So this is the filtering action of capacitor. So you can see here I have drawn the capacitor, how it is working. So directly using one capacitor or one inductor, we cannot get pure DC. Slowly we have to move it. That means if you increase more value, more capacitance value, then you can get more smoothness in the graph. Okay, this is for capacitive filter. The same concept will be used in inductive capacitor. So this is a detailed diagram. This is for half-wave rectifier, this is for full wave rectifier. Okay, so full wave rectifier means we'll get like this. Okay, and if you detect the envelope, fully charged, then discharge, then fully charged, discharge, charge, discharge, like this. Okay, now if I do more to that, then it will be like this, like this. Now if I do more to that, then now see, from first to second to third to fourth, the ripple is reduced, or I can get like this type of waveform. Okay, so always remember, capacitor, any filter, maybe capacitive, inductive, anything, it is not 100% perfect. We have to cascade, means connect 2-3 stage of filter, then only I can get a pure DC signal. Now inductive filter, you see it here. We have understood the capacitive action, inductive action. Now see, we are giving AC plus DC here. Now what is the property of inductor? Inductor will pass DC, block AC, or pass pass AC and block DC. Which one?
Pass DC and block AC.
Pass DC, block AC.
Block AC.
So AC will be block across capacitor, inductor, and DC will be pass here. So DC will pass here means we'll get some voltage here. But remember, it is not fully blocking the AC. Okay. Fully blocking means if it will provide infinite impedance, then only it will fully block. XL equals to 2 pi FL. So it is finite. Okay. So somewhat AC is blocking and small portion of AC is still going to load. So that's why the rippleness is somewhat reduced, but it is not perfect. So I'll get like this. if I take inductive filter. Okay, so you can see here previously it is more ripple, now it is somewhat less ripple. Okay, but we cannot say it is perfectly pure. Then we combine both the things. Means you see here inductive filter, capacitive filter, both are combined. Inductor are connected in series, capacitor connected in parallel. So first inductive action will come into picture. So we'll get last example we have seen like this we have got. Okay, then capacitor action will take place, so it will be more smoother. That means the output will be, if I consider here this is as my input, then it will be like this. So compared to 1, 2 have less ripple. So this is your LC filtering action. Okay, so it consists of inductor in series and capacitor in parallel. The pulsating output is applied to filter. Inductor offer high opposition to AC and pass DC component to capacitor, which appear across the load. Now this is one part. Okay, we can use only capacitive filter, only inductive filter, LC filter. If I want more smoothness, I can use another capacitor here. That means first capacitor action will taken place, then whatever left out, it will go to inductor, it will again process, then again capacitor. So that is called as LC pi filter. You see here, the structure is generally we write pi like this. So here one capacitor connected, here one capacitor connected, here one inductor is connected. The structure is like pi, so it is called as LC pi. So if you take this circuit, then you may get a waveform like this. So if you look at from very far, it is like a straight line. Okay, very small ripples are there. And even if you not satisfied with that, then you can combine two capacitive filter, two LC filter like this. Capacitor, inductor, then capacitor, then again capacitor, again inductor, then again capacitor. So this one, first one is filter 1, this is filter 2. Okay, this is called as cascading of filter. Okay, so that depends upon the requirement. If you want more and more fine or pure DC, then we can cascade the filter. But within this L and C, if we require very easy or we can say less cost, then a capacitive filter is more useful because the capacitor is not heavy compared to inductor, because the inductor means what? Coils are wounded over iron core. So weight of this inductor are high, or also the cost is also high because the wires, copper wires are costly. So inductive filter is not preferred over capacitive filter. Capacitive filter are more preferred. Okay, but that depends on purely application. If you require more pureness, then you can you have to go for cascading of this filter. LC pi or cascading of LC pi, you can go. Otherwise, simple analysis, you can take capacitive filter. Okay, so in lab also you are doing this capacitive filter for easy understanding and for easy analysis. Yes or no? Have you done this one in the lab?
No, sir.
No, sir.
Rectifier is not over, so maybe next class you will do diode characteristic over.
Yes, sir.
Yes, sir.
Next lab we will do this one. Okay.
Yes, sir. Okay, sir.
So that's it for today.
Sir,
Yes.
can you share this?
After the class I will share.
Sir,
Please send this, sir.
PPT, sir.
PPT I am sharing. Na, I have not checked.
Sir, journal, sir. Can you share the journal?
सर
क्या बोल रहे हो?
सर सैप पोर्टल पे सर मेरा एक एब्सेंट शो कर रहा है सर, बाकी
सर,
सबका
सब
फुल
क्या
प्रेजेंट
कर रहे हैं?
नहीं नहीं
यस सर,
सबका
स्टार्टिंग से सब कुछ ठीक है।
भाई एक दो अटेंडेंस कभी छूटेगा, कोई ऐसे इशू नहीं है।
ओके सर।
वो क्या शेयर करने के लिए वो बोल रहे हो तुम, समझ नहीं पा रहा हूँ।
टुडेस क्लास नोट सर,
आपका सर हैंड रिटन वाला
हैंड रिटन नोट सर आपका वाला।
Yes,
Hand
sir,
written वाला?
journal, sir.
और ये वाला तुम्हें समझ में आएगा क्योंकि मैं बहुत बार उसको चेंज कर
सर
देता हूँ
समझ
ना।
आ जाएगा
ये
सर।
सर हम समझ लेंगे सर।
यस सर।
क्योंकि तुम देखो ये तो शुरू से ही है, मुझे कोई दिक्कत नहीं है भेजने में। जैसे कि ये है ना, ये तो शुरू से ही है, लेकिन कुछ कुछ चीज है कि मैं उसमें जैसे कि आज ये पढ़ाया रेक्टिफायर, हाँ ये वाला आज क्या पढ़ाया, पीआईवी निकला ना, पीआईवी में फिर से मैं
सर।
उसमें जाके पुराना जो ब्रिज टाइप में उसे चेंज कर दिया इसमें। तो इसको अगर समझ में आएगा तो मैं दे दूंगा।
यस सर प्लीज शेयर कर दीजिएगा सर।
ओके, आफ्टर द क्लास आई
यस सर प्लीज सर।
so that's why I'm telling you should running note if you prepare, that is good. Otherwise you can ask me, no problem. Okay, after the class I'll share. Okay,
यस सर।
थैंक यू सर।
so we'll wind up the session for today. I have taken the attendance. Thank you.
Okay, sir.
Thank you, sir.
थैंक यू सर।
थैंक यू सर।
Thank you, sir.
थैंक यू सर।
थैंक यू सर।
थैंक यू सर।
Sir.